In this video, we are going to talk about the ground state versus excited state, and I have these pre-written out. So the ground state is the normal electron configuration that's found on the periodic table. So when you look up configurations on the periodic table, all of these configurations on the periodic table that you see written at the bottom of the symbol are the ground state. They are the lowest possible energy state that the atom could be in. The excited state is exactly what it sounds like. It's a state where the electrons are in a higher orbital than they should be, or higher than the ground. All right, and the reason it's called excited is because it has gained energy, and therefore the electrons have become excited and jumped up, just like people when they get excited. I guess you can kind of use that as an analogy. Maybe it works, maybe it doesn't. But basically, the electrons are in a higher energy state. And this is why, if you remember back from the last lesson, when I said that the orbitals could also be called energy levels, this is where it comes into play. The orbitals are energy levels, and if you're in orbital 1, then you are in the lowest energy level, meaning you have the lowest energy. If you were to jump to orbital 2, that means you have a higher energy. Basically, you have to have energy that matches the orbital to hang out in that orbital. So if an electron jumps to an excited state, a higher energy level, then it must have gained energy, because it would not be allowed in that orbital if it didn't gain energy to do so. We'll explain that at the end as well. But drawing them out, very easy. Watch. This is the way I want you to do it all the time. Take the valence electron number, which you should know from the ground state, which is always just the last number, and take one of those electrons away and bump them up into a higher orbital than you wanted, or than they currently are in. So for example, 281. If I took one away from the 8 and put it into the next orbital higher, my new configuration would be 271. That's an excited state configuration. Now, be aware, if you see this on like in a problem or on Regents or something like that, that's not the only excited state configuration. You could, in theory, take one from the first orbital and bump it up to, oh, I made a mistake there. You could take something from the first orbital and put it in the third. So you could have 181. That is also an acceptable excited state, although I will not take it on a test. I never want to see you do that. But be aware that if you see that on a paper, that is a legitimate excited state. You could even do this, 2701. You could take one from the valence and bump it up 2 or 3 or 4. There's no limit, right? But things you can't do. You can't take, in this example, one from the first orbital and do this. Made another mistake. You can't do 1, 9. And the reason you can't do it is because there are maximum number of electrons that can fit in the orbitals. And so the second orbital can hold a max of 8. So if you say 1, 9, that's physically impossible. It's got to be wrong. All right, so the way you avoid that is by doing it the way I'm doing it. Take a valence and bump it up into a new orbital. You will never have to worry about overfilling that orbital, and therefore you don't even have to worry about the numbers needed to overfill it, and it's one less thing to worry about. That's why I want it done that way every time. So 2, 3, you just take one away from the 3, and it becomes 221, 285, 2841, 27, 261, 281. What do you think? If I take one away from 1, what do I get? 2801. That's fine. You can have a 0 in there, just like I did over here. You're doing the same thing every time it works. Okay, so that's the way I want to see you do it on any tests or quizzes or worksheets or anything like that. You can also do excited state and ground state using Bohr models. So for example, this is calcium, right? This is the calcium in the ground state. This is calcium. This is going to be calcium in the excited state. Okay, it should say, that was just, the document must have ran out of space. So if I were to redraw this in the excited state, here's the easy thing. It looks like a lot of work. There really isn't. Just focus on this. What would the configuration change to? It would be 2882. So if I take one away from the valence and then rewrite it, and you're done. And I didn't do it here, but you should always write the E's in. And then the nucleus, well, the nucleus has nothing to do with excited state or ground state. So that's never going to change. Well, this one says 21. So 21N. Okay, I wrote 2020 just because I'm so used to using the calcium that's on the periodic table. So that's something that you really should be careful of. You get into a habit of calcium always weighing 40, and then they throw something in and it doesn't work. So just be aware of that. And then the last one. So we'll do it a little differently. We'll draw the nucleus first. That's never going to change. It's really just 2, 8, 3. What changes? And always write the E's in. I won't accept it on a test or quiz if the E's are not written in. All right, and so that's it. That's how you do excited states using Bohr, and that's how you do it based off just configurations. Now, next part. This part, yes, I cheated. I have these pre-printed, so you're going to have to write them out. Your notes are going to be much more blank than mine. Sorry, but deal with it. So this is what yours are going to look like. Well, they're going to look like this, like a big giant blank page. And when they're done, like magic, it's going to look like that. So let's go over it. So this is the process that causes what we call excitation and relaxation, okay? So this is what causes an atom to go from the ground state to the excited state. That's the excitation process. And then relaxation is when it drops back down to ground. So think of it like a person jumping out of their chair and then being like, that was too much work, I'm gonna sit back down. And that's pretty much what happens. So there's an easy way to remember it: in, up, down, out. And what it refers to is the energy goes in, the electron jumps up, the electron falls down, the electron goes back out, or the energy goes back out. Now, energy in, what does that mean? That means that the energy gets absorbed by the atom, or by the electron specifically. And now that energy, that's step one here, I have it color-coded pink and pink. So energy in, or the energy is being absorbed. So I use a little squiggly line to show the energy. It could be electricity, it could be heat, it could be something else that I don't know of, but I'm sure there's different types. But it's typically heat or electricity, mainly electricity. But that's what makes that's the first step. So the energy comes in, the electron absorbs that energy. Now remember, I said these are energy levels. They're also called energy levels, not just orbitals. To be in orbital 1, you need to have energy that matches orbital 1's energy. Well, once this electron absorbs energy from the outside, it no longer has the energy that corresponds to orbital 1, so it's got to jump up to orbital 2 because now it's got the energy needed to be in orbital 2, so it has to be in orbital 2. It gets there and it says that jumping up, we call that the excitation process. Now be aware, it could jump up 1 orbital, it could jump up 2 or 3 or 4, there's no limit. As long as it goes up a orbital minimum, then that's all that matters. Once it gets there, it says, meh, this is too much work. I don't like doing this, because if you're in a higher orbital, then you have to do more work and so on, and so there's no way around that. So it doesn't like it. So it gives back the energy that it just absorbed. So that is the energy out. Now, I'll explain why I have them misnumbered in order. It's just, I guess, the way I explain it. So the energy gets released in the form of light now. So just be aware, the energy that was absorbed was heat or electricity. The energy coming out, it's the same amount of energy, but it is now light energy as opposed to heat or electric energy. So be aware of that. That's going to become important in our next topic. And then once it does that, it falls back down to its ground state, and we call that relaxation. So turns out in real life, steps 1 and 2 happen at the same time, and steps 3 and 4 happen at the same time. So by absorbing the energy, the electron is jumping up, and by falling down, the electron is releasing the energy. So that's why the order matters to a degree. In other words, as long as you have the 1-2 step first, and then the 3-4 step, it does not really matter which one comes first and last. Turns out it's really a 2-step process, but when I used to teach it as a 2-step, people always confused it for some reason. I don't know why, so I broke it up into 4, and it seemed to work a little better, okay? And last part. Steps 1 and 2 are fully invisible, meaning we can't see that at all with our eyes, right? But steps 3 and 4 are the visible part of this. So the 3 and 4, it gives off light. That light is what we can see. That light is actually called a quanta. A quanta is a specific amount of energy, and this is where the concept of quantum mechanics or quantum energy comes into play. I can explain that more in person if you have questions, but basically here's what it means. The electron has to absorb the exact amount of energy needed to get to the next orbital. If it doesn't absorb the energy needed to get to that orbital, the exact amount needed, then it doesn't absorb the energy at all and nothing happens, all right? And that's pretty much it. It's like if you're trying to, I don't even know, like you're on a playground and you see the parallel bars and you got to jump to grab them, right? If you're like 1 inch too shy and you can't reach that thing, what happens? Well, gravity happens and you fall back down. And it's kind of like that. Although it's not a gravity-driven thing, but that's the idea. The electron has to have exactly the right amount of energy needed to jump up to that next level. If it misses it by a tiny little bit, then it's going back down and nothing's going to happen. Last bit, why do we care? Some of you may not at all, but for science purposes, why do we care? Here's the reason why. Turns out the light that gets given out creates a bright line spectrum. Bright line spectrums are unique, and this is another example where I have it pre-written, sorry. That light creates what's called a bright line spectra. That is a pattern of light that is unique to every atom and every compound ever. So after hearing that, you should be able to hopefully understand how valuable that is. So it's basically like DNA or a fingerprint, but for a molecule or an atom. That's pretty much it. It is unique to that atom. It is unique to that molecule or compound. And it can be seen with just light, which means you can, relatively easily look at it. So it requires a spectroscope. It's like a microscope, but for spectra, right? So it's a microscope looks at really tiny things. Spectroscopes look at the light that comes off here and break it up, and so that you can see the bright line spectra. It's like a fingerprint for the element. And so it's going to look like a barcode. Like, when you go to the store and you got the barcodes, not the QR, the old school barcodes that just looked all the black and white lines, right? Except it's going to be colored, and it's going to be colored the colors of the rainbow, meaning like Roy G. Biv, the red ones will be over here, and then eventually orange, yellow, green, blue, indigo, violet. So as you go along, the colors of the bars will eventually change depending on where their location are. What those lines represent is a unique energy transition, meaning every time an electron falls a very specific amount of orbitals, it'll create one line. So like, for example, if the electron dropped from orbital 2 to orbital 1, you get that specific line. If the electron were to fall from 3 to 1, you get that line. 4 to 1, you get that line. And now granted, this is a very simple one because I'm only showing you if everything just fell down to orbital 1. But there's no rule that says that. There could be, from 6 to 5, it could fall. It could fall from 5 to 4, and those would also create more lines. So sometimes bright line spectras look really complicated, and sometimes they look really simple like these down here. These are black and white versions of bright line spectras. If you saw them in real life, they would be colored, but that's pretty much it. So turns out each set of drops creates what's called a series. And here's what they look like. So this one's in color, so hopefully it looks a little bit better. But these individual drops, and there's more than just these, but these are like just the easy ones to explain. They'll create these series of lines, okay? And so if the electron were to fall this far, it makes that line. If it falls this far, it makes that line. This far, it makes that line. Hopefully you get the idea. And when they're done, they look like this. And in this case, the red was on the right, and then the violets were on the left, but you should hopefully get the idea. It doesn't matter if I flip it or not. But this is what they look like. I will attach an additional video from a different source that should hopefully show you actual bright line spectra and what they're used for, but really it's for identification purposes. In other words, it allows you to identify elements. It allows you to identify compounds that you wouldn't necessarily know what they are. An example would be if you're a detective and you go to a crime scene, right? And you see a white powder and you're like, well, what's this white powder? And a lot of people might think, oh, well, it's some drug. But it could be some poison too, or it could be like chalk, and then it's nothing, right? Well, you're not going to taste it, so how do you figure out what it is? Well, you put it in a machine that creates its bright line spectra, you analyze the spectra, and then you compare it to a database, and once you get a match, the computer does all that part, once you get a match, you know what that material is. And that's the real use, or one of the main uses for this.